the University of Saskatchewan presents Unitel, a program of information, research, and development.
Signal light's good. Good. Tail light's good. Brake light's good.
Engineers at the University of Saskatchewan have been working on this unique little car for more than 3 years. What began as a design project for a master's student has become a flagship project for the College of Engineering, involving countless students, staff members, and faculty, and capturing the interest of people across the country. The car is called Nexus, and it is designed to provide a safe, fuel-efficient alternative for commuters of the future. A single-passenger car, Nexus is designed to meet the existing Canadian safety standards for passenger cars. It will go 200 miles on a single gallon of gas, and despite its ultralight construction, it will protect the driver in a collision at 30 miles an hour. Commuter cars similar to Nexus are produced in both the United States and Japan, but the Saskatchewan version offers much more.
The reason why these are not permitted to be sold in Canada is the fact that they are only motorcycle safety compliant. In other words, the safety provided by these foreign-built cars is essentially much the same as that provided by a motorcycle. Our vehicle is going to withstand a 30-mile-an-hour barrier impact test just like a normal car. It'll have a side door intrusion capability. It'll have crushing strength in terms of rollover on the roof, and these other safety standards require quite a bit of additional work in terms of getting the fuel consumption up high and the safety up high at the same time.
Professor Barry Hertz has been working with the Nexus project as a faculty advisor since the beginning. He's only one of the many faculty, students, and staff who've added their ideas to this practical and educational project.
Well, we really have 3 full-time engineers working on the project. We have 3 summer students, 3 faculty advisors, and we've a steno and 2 technicians. So we've got quite a large, there's 12 people altogether contributing ideas and working on this. Plus, the vehicle itself is being built in our engineering shops. So it involves the technical machining staff and so on, electronics people and so on from the central shops here in engineering. So it interfaces with probably up to 20 individuals at the University of Saskatchewan.
Nexus has been a unique training experience for the many young engineers working on the project. For the central design team, building the first Nexus prototype under a contract arrangement with Transport Canada was a lesson in automotive design and construction that could not have been learned in the classroom. And for junior engineering students, it led to assignments that were both practical and necessary.
As Greg was saying, one of the most important parts of the Nexus vehicle is aerodynamics. And so thus we have to find a mirror that would be very aerodynamic in the wind. The first shape we looked at was a simple sphere. And when studying the effect of high wind on the sphere, as you can see, there's quite a lot of turbulence forming from behind the sphere in the wind. So we thought that this wouldn't do for a shape. The most aerodynamic shape we could find was that of the teardrop shape right here. And perhaps you can visualize this: when a drop of water falls, the shape it takes on the way down would be the most aerodynamic or efficient shape on the way to the ground, and that's the teardrop shape. Okay, that's a very aerodynamic shape. As you can see, the wind follows the teardrop all the way around and then resumes its normal flow on the other side, and there's very low turbulence in here. But this shape, of course, wouldn't be very practical for the mirror itself, because we can't mount the mirror on the end of this.
So many educational experiences involved with this Nexus project that it's hard to really begin singling them out. To begin with, we've had 3 master's theses completed on the car. Some of them are just in the final stages right now. And so from the graduate studies point of view, it's been very helpful and a good learning experience for some of the people. And then we've also had our project engineer and various other of our research engineers learn a lot about manufacturing processes and that type of thing. Until this project came along, we had very little knowledge in how to work with composites and fiberglass, Kevlar, that type of thing. Plastics have been used extensively for the body of Nexus, which was a very good learning experience for all of the people involved in that aspect. And we've also learned a little bit about the techniques of negotiating contracts and getting along with other people and so on in a contract situation, which was a new experience for many of us as well.
There is room for only one person in the tiny 3-wheeled Nexus. An aerodynamic fiberglass shell encloses the driver and the single rear wheel, and the front wheels sit away from the body in streamlined fairings. The car's modified all-terrain vehicle engine is mounted behind the driver's seat, giving it enough power to keep up with regular highway traffic. To protect the driver, there's a wraparound bumper and a solid foam nose section designed to absorb the impact in an accident. The graduate engineers who have designed and built Nexus are only too familiar with the problems that can arise in building this kind of prototype. While some of the car's components were available on the market, many had to be manufactured from scratch. Research engineer Dave Gerwing found there were always modifications to be made to his original design.
I think one of the things in design that's always difficult to accept is, I guess, in order to really achieve any good design, you have to fail. And one way to achieve better and better designs is to sort of double your failure rate, if you like.
Well, when you work with design concepts, and often in education you leave the thing as a design concept and possibly make some drawings but never actually have to build it. Whereas in this project we actually had to build the prototype and fabricate it and road test it and so on. So it got us to go considerably beyond what you'd normally expect to do in terms of like undergraduate design work and that type of thing. The only existing components that we used pertain to the powertrain. Pretty well everything, the wheels and the axles, the suspension, and the way the body goes together in the frame and all that stuff, even the brakes. Some of the brake components were off-the-shelf motorcycle components, but most of the other things were handmade, and often handmade several times in order to get something that was satisfactory. And so it involved a real major effort in terms of fabricating things in our shop.
The first step in designing the Nexus car was perfecting the car's aerodynamic shape. The engineers used the university's massive wind tunnel, a giant simulator that measures the forces of air pressure on scale models. Components, like this streamlined wheel fairing, were mounted in the airstream, and computerized measurements were taken to calculate the aerodynamic drag. Once the best shape for the overall body was determined, the engineers used the wind tunnel to learn other things about their car.
This is a wind tunnel model that we've been working with for the last couple months or so. And the purpose of this model is to measure the air pressure on the outside of the model, all over the body. So to do this, we have little pressure taps all over the place, and these are just openings in the model that are connected to little rubber tubes, and these in turn are connected to the computer where we measure the pressures. Now the purpose of measuring all of these pressures is so that we can find out where we can put inlet ducts for engine cooling. We have an engine that sits right back in here that needs to be cooled by air. So if we know the air pressure on the outside of the model, we can decide where to put inlet ducts to let air in at a high pressure region, and we know where to put outlet ducts at a low pressure region. We did a lot of work, and I did a lot of analysis on this, and after trying a few different things, we found the only really place we can bring air in is right up here in the front of the car, right in front of the windshield. This corresponds to a lot of the inlet ducts you see in passenger cars for occupant heating. So what we're planning on doing is bringing air in here, ducting it vertically downwards, and letting it out back in here. We have a high pressure region here that pushes the air in. We have a low pressure down in here that pulls the air out. But there's only one problem with this. The engine's back in here. So what we've had to do is we're mounting a small heat exchanger, and we're pumping the engine oil all the way forward to this little heat exchanger, running it around the heat exchanger and then pumping it all the way back. And this way we can take part of the cooling load of the engine. We can't take all of the cooling load, unfortunately, because we're limited as to how much heat we can dissipate with a cooler like that. So what we've also done is we're putting an inlet grill right in here on both sides of the car, and we're forcing the air to come in this with a fan. And we have a fan mounted inside, in front of the engine. It pulls the air in on either side of the car, past the engine, and then we get rid of it back in here again. We have another outlet grill. And that fan is driven electrically and from the battery. So we have a two-fold system. We have an oil cooler up front, which partially cools the engine, and we also have a fan mounted in the back to force the air over the engine. One of the advantages of having an oil cooler up front here is that we have a source of heat at the front of the car to warm up the occupant compartment.
With the wind tunnel testing out of the way, the engineers turned to the task of actually building a full-scale working prototype of the Nexus car. They built this machine, called a digitizer, to make an accurate full-scale copy of their wind tunnel model.
Well, the digitizer has 5 axes of movement, and what we're trying to do at all times is tell the computer the exact location of the tip of this pen at any one time. So to do that, it has to know where it is in the Y direction, also in the X direction, the length of the car, and in the Z direction, the height of the car. The other 2 degrees of freedom are the theta direction, which is just an arbitrary name that we call it. It's to allow us to do sloping surfaces, as well as the omega direction, which allows us to rotate the model to do planes of the car in this direction. To do a digitizing step, what we do is set the pen on the model at a place where we would like to begin. Then we start the computer and follow the model in the direction that we're concerned about. All the time, the computer is reading the position of the tip of the pen through the voltages of the potentiometers at any time.
The computer prints out 2-dimensional patterns of various planes of the model. These paper patterns, full-scale pictures of cross-sections of the Nexus car, are used to construct what the engineers call a body buck.
Well, this is what we call a body buck. It's in the process of being constructed now. And we got these templates from digitizing this model, which is what Brant talked to you before about. This part here is essentially the bottom of the car. So from the bumper line to the bottom of the car, it's a model of that in full scale. And what we're going to do with this is cover it with plywood and strip wood and then body putty it and give it the final finish that'll be exactly the same as what the car will be. And then from this body buck, we'll take a mold off it with fiberglass, which would be like a big bathtub, a negative image of this. And then inside that, we'll produce the actual car bodies out of fiberglass, a composite material. So it's essentially like building a boat the same way they do that, except we're applying it to building a car.
After we spent some time in the wind tunnel and come up with a model that looks like this, that we know is a good aerodynamic shape, well, we have to build that full scale. So to do that, we use a fairly standard boat building technique. We build a male plug, which this is called as a male plug, and this will be an exact replica of what the body is going to look like. What we do with this is we get it perfectly smooth, we paint it, and then we cast a mold from this body buck. And the mold is made out of fiberglass, and the fiberglass is applied to this body buck all over the place in about 5 or 6 layers. And then we separate the two halves. And you have the body buck and you have the mold. And it comes apart, and then you have what's called a female mold. And from that mold, we can make the actual bodies of the car by laying out fiberglass inside that mold. So we go through this whole process of making a body buck, which is this guy, a female mold, and then we can actually turn out pieces.
Now, are you ready to roll? There. This stuff peels off, exposing a beautiful surface underneath.
The fiberglass body encloses the driver, the engine, and the rear driving wheel. Inside this shell are the special safety features that make the tiny Nexus as safe as larger cars on the road. Bob McEachran has designed a special foam nose section to protect the driver in a head-on collision.
This particular design is a solid nose made of layers of polyurethane foam. The foam is used as insulation, but I found that it has very good energy absorption characteristics. So as the foam is crushed, it absorbs a lot of energy. This is definitely a preliminary procedure to find if this design will work. If this car was ever going to be certified for sale, they would have to test full-scale models, actually build full-size prototypes and collide them with a brick wall.
Scary, eh?
It's a quarter scale tester. What that means is I only need 1/4 of the velocity, which is much easier to achieve than full velocity. I have a 1/4 scale model, and I have 1/4 of the mass of the car. So the hammer only weighs about 200 pounds, and it only travels at about 8 miles an hour when it strikes the plate. So in a sense, essentially it's just a swing with a big weight on it. The idea is for it to completely destroy itself and absorb energy. If you're in an accident, it will be taken off and thrown away, and a completely new one will be put on the car. The one main attraction of this foam is it's very low cost, and to replace the front would be, well, very, very low cost.
Similar tests were needed for the many other specially designed and constructed components of the Nexus car.
Many of the components, the structural components on the Nexus vehicle, because of the aerodynamic requirement, the fact that they have to be very small, and also due to weight restrictions, they have to be very light. We couldn't just go out and grab a part from a Honda or from a Chevette or something and have it hope to fit on our vehicle. Therefore, we did have to go right back to the basics, figuring out what the loads were, and from the loads, then calculating stresses either by computer or manually. And then the ultimate test, of course, is whether you can set the thing up in some kind of a jig, simulate the actual road loads on it, and see whether it stands up.
The engineers built several versions of the upper A arm, the aerodynamic strut that holds the car's front wheels away from the body.
The part that we see up here, if you like, is what's actually setting inside the car, all right? And this part is out in the airstream, and the actual wheel attaches on, and it would be sitting out here. And so there's a lot of bending that goes on in this particular member right here, and this is one of the things that causes it to fail. It pivots right at the plus sign there, if you like, and this wheel is shown in the maximum downforce or maximum bump or rebound position, and this wheel is shown in the maximum actually upright position. That's as far as our suspension can compress, and our total suspension travel between those two is about 6 inches.
Several A arms failed to meet the required specifications, but eventually the engineers came up with a design that worked. Like the A arm, the car's unique hub assembly was built from scratch, and the internal aluminum frame was cut and welded by hand. It took many months of designing and testing and failing to get the Nexus commuter car on the road. And even though it's up and running, there are many questions left to answer. The completed car will make its debut at Expo 86 in Vancouver. As an extremely fuel-efficient car, it will be part of the Transport Canada display on alternate fuels and energy systems. When it returns to the U of S, it will undergo further studies.
Right now we're doing the analysis on the car. We're going to find out what the limits are for fuel consumption, for crash worthiness, and so on. And we expect that there will be industrial spin-offs on vehicles of this type. The university naturally isn't involved in producing consumer-type vehicles. But there's been considerable interest already shown by various companies involved in the automotive industry, and they're well aware of what's going on at our university. We expect not to build any more vehicles like this immediately. They're very expensive to hand build, and we'll be getting as much data as we possibly can from the one existing prototype. And then if the situation requires the construction of several others, we'd certainly be open to that type of extra activity. And I would expect that by the turn of the century, you'll see all sorts of vehicles on the highway that resemble Nexus in one or more ways. I would expect you would see a lot of three-wheel type vehicles, single-passenger vehicles, and very fuel efficient.
If you want to know more about the University of Saskatchewan, please write us at Unitel, Kirk Hall, University of Saskatchewan, S7N0W0.